to uh, get into the main body of the lesson, we need to recap some of the facts that we learned before in the high school. That is Ohm's law and application of Ohm's law to a voltage divider. Ohm's law says that current through a closed circuit is directly proportional to the potential difference, unit voltage. We can say voltage V equals I times R, where I is the current flowing through the circuit and V is the potential difference in volt. And R is the proportionality constant. We call it as resistance of the circuit. We extend the Ohm's law by adding a second resistance into the circuit. Now we can see same current I flow through two resistances. But the difference here is now we are having two separate voltages in circuit. The unknown voltage Vx we can find, that is current times resistance. I is Vs over R1 plus R2. So voltage Vx is I times R2. So equation 4, Vx will give you Vs R2 divided by R1 plus R2. Now ready to visit the amplifier using a block diagram, using voltages, resistances, and currents. Now you can see on the figure, there is an input port and an output port, and there is no connection from the input side to the output side. So if you need to have a current flow, we need to have a source at the input and a load at the output. The other thing that we see is a dependent voltage source AV times VI. It is called a dependent voltage source because AV is the gain of the amplifier getting multiplied with your input voltage to make an internal voltage source a dependent voltage source. Or we can connect a signal source at the input and a load at the output. We need to see how a voltage source is represented electrically. Figure A illustrates how a voltage source can be represented electrically. A voltage in series with its internal resistance. Every source has a built-in internal resistance. We call it source resistance. The internal resistance can limit the flow of signal current in a given circuit. Remember, it can only limit the flow of signal current. It cannot stop the flow of current. Moving to the loudspeaker. Loudspeaker is represented as an equivalent resistance in electrical engineering. Now that we are familiarized with all the required information, we are ready to explore a loaded amplifier. It is loaded with a signal source at the input and a loudspeaker at the output. Here we see amplifier input is loaded using a signal source, that is Vs in series with Rs and Ri now. We can see it is a voltage divider. So we can find out voltage Vi using voltage divider expression we have seen earlier. Equation 5 shows that. The point that we are going to notice here is now we can see Vi is smaller than Vs. So there is Vi is only a fraction of Vs. Looking at the output circuit, we see AV times Vi in series with two resistors. And equation 6 is expressing V naught, which is AV times VI RL divided by R naught plus RL. Kindly notice V naught is smaller than AV times VI. Now we are going to substitute equation 5 into equation 6. So equation 7 is going to show us the overall voltage gain. Now equation 7 is reproduced here for convenience. The overall voltage gain is having three separate terms. First is the unloaded gain. The second term is called attenuation due to RS. Why we call it attenuation? Because look, it is a fraction. If we really wanted to understand on the second term, put RS equal to 0, this fraction is 1, the highest possible value. If RS is greater than 0, the value of the second term is less than 1. Similarly, looking at the last term, you can see the denominator is more than the numerator. It is a fraction. If you put R naught equal to 0, we get this fraction equal to 1. That is the highest possible value. Now, notice that here, Ri and R naught, that is the input resistance and output resistance, are design parameters of the amplifier. That means a designer has some kind of a control onto those values. But Rs is a part of the source. We have no control. And RL also, we don't have a control. It's an external component. First, attenuation due to RS is reproduced here. Attenuation due to RS is a fraction. Its value is less than 1 because RS is not equal to 0. But we still need our overall gain as high as possible. What can we do? RS is part of the source. We have no control. The only possible way is a designer can choose Ri very much greater than Rs. In this case, this fraction will get close to unity. The attenuation due to R naught is reproduced here. We can see here again a fraction. But we need the overall gain as maximum as possible. R naught cannot be a 0. Therefore, what better thing that we can do? We can, as a designer, choose R naught very much less than RL. In this way, we can get this fraction close to unity.